technology adoption and bringing new technologies to help construction companies with more efficient scheduling. So with that, I'll start the presentation. As Tom briefly mentioned, our vision is revolutionizing the concrete industry and construction industry in general. Our vision is to be able to monitor concrete throughout its life cycle, all the way from the beginning when concrete gets mixed in the batching plant and is delivered and placed in the job site, and after that, while it's finished and cured and hardened, and all the way through its life cycle when concrete structures are in service, so that we can monitor concrete performance and behavior and properties and bring that data in real time in the hands of different stakeholders, so they can make more informed decisions on the state of concrete and the critical operations that goes with it. But today's presentation is focused on earliest stage construction, where you're dealing with building new structures and you want to know how concrete is curing and hardening, so that you can optimize your schedules. To give you a background, I'll start today's presentation on essentially how we're measuring concrete strengths today, and you're familiar with the cylinder test for sure. And I'll introduce some other test methods that can be used instead of Brecht test, and concrete maturity in particular will be the subject that we'll expand on it. I'll go through the standard specifications, the concept behind concrete maturity, how you can calculate concrete maturity, and how you can use it in the field to measure concrete strengths in real time, and basically in lieu of concrete cylinder test. And after that, I'll introduce the new advancements. Concrete maturity, by the way, is not a new concept. It's been in the works and the standards for more than 30 years. But at the end, I'll introduce the new technologies that leverage concrete maturity in a very efficient and simple way to bring real-time strengths monitoring in your hands. And I'll follow up with some case studies on how these technologies can be used in different applications. And after that, there are some suggestions on how to start with maturity in your next concrete pour. So before that, the whole concept of in-situ monitoring of concrete strength goes back to early 70s, where we unfortunately had a collapse in a skyline towers in Fairfax County. It was a progressive collapse, and the investigation that was started after that collapse that unfortunately killed 14 workers on job site concluded that the premature removal of formwork before concrete gained enough strength resulted in the collapse of that particular slab, and then after that it was a progressive collapse. And in 1978, there was another collapse in a cooling tower in Willow Island where almost 50 workers died on scaffolding, again as a result of premature formwork removal. And these investigations that started after these incidents led to the development and standardization and documentation of accurate method that can be used in the field to monitor concrete strength. And I'll get into the details of why Brecht test is not really sufficient in several cases, and how other methods can be used to accurately monitor strength development at the early stages of construction. So this is how basically new methods were emerged, and obviously these are all to address the measurement of field strengths of concrete that is required for critical operations, including formwork removal, post-tensioning, where you want to know when to exactly pull the post-tension cables. Curing optimization, for that matter, you can optimize the amount of heat that you apply to your structure based on knowing exactly what the strength is there. Saw cutting, you don't want to do it before concrete has enough strength. And opening traffic on concrete pavement, where especially you're doing repairs on concrete pavement or fast track projects, you want to know when exactly you can open traffic on that lane. So all of these are dependent on knowing the strengths and accurately, quickly in situ. And as I mentioned, different test methods were initiated and developed as a result of incidents that I showed earlier. So we'll get into that. But how we're measuring the strengths today. So basically, concrete is mixed in the batching plant, as we all know. It's delivered to the job site. And at the job site, there are two sets of cylinders taken. One set of cylinders are basically standard cylinders that are sent to a lab for conditioning in a standard curing conditions, and these are for acceptance purpose. And the second set are sitting on the job site, basically either field cured or CPOC specimens that you may use to have cylinders that are basically mimicking the condition of the structure. And these field cure cylinders are staying in the field until whenever you decide to send them to the lab, and the lab would take those cylinders, break them, and get the results back to your job site. And this is what you would basically use for formwork removal, post-tensioning, or those critical operations that are dependent on knowing the strength of concrete in situ. So obviously, there are different limitations associated with this process. The first one is curing temperature. The cylinders that are cast and sitting beside the concrete element on your job site are not exactly going or undergoing the same condition as your slab. You may be putting them underneath the slab or beneath the heat blankets, but they're not necessarily experiencing the same temperature as the concrete in the slab itself. And as you know, the difference in the temperature that is applied on the concrete can result in different strength values. Secondly, the whole process is inherent delays in it. By the time you make a decision to send one of these specimens to a lab, you need to call the lab technician to come and pick up the specimen, go to the lab, break the sample, send the results back to you, and you'll be losing half a day or a day at least for pour, and you'll be sitting there while your concrete may have already achieved the targeted strengths to go to the next step. There's obviously limited information associated with breaking one field cure cylinder, and these cylinders are basically thrown in the back of a pickup truck at day 1 or day 2 or day 3, and that's too early for concrete to go through that shock basically, and you may experience micro cracking in the concrete. The concrete may not break well in the lab, and that one cylinder or at best 2 cylinder may not give you the accurate information on what's going on in your structure. The other thing is that these cylinders are sitting in one corner, and that's not obviously capturing the local strength variation across your structure. So the corners of the structure may be exposed to cooler temperatures and may develop strength at a lower rate compared to inner parts of your structure. You may have thicker slabs or thicker columns that may gain more strength as opposed to the thinner elements. So those variations across your slab cannot be captured by one cylinder sitting beside your structure. And obviously, because of all this, you'll get low visibility into what's going on in the curing and hardening stages in your concrete, and because of that, most contractors and GCs they play conservatively and wait longer than needed to go to the next step. Okay, and if you have a cylinder that doesn't really break well, this may end up to be the situation. This is actually a post-tension structure where the cables were pulled too early, and all the concrete cover was popped up open. Again, this is showing that even if you have cylinders, not being able to capture the actual strength development inside the concrete can result in catastrophic damages. Okay, what are the options and alternatives instead of break test? Well, over the past decades, standard bodies and committees and researchers have developed different test methods to accurately capture strength hardening in concrete and not rely solely on break tests. So there are different non-destructive test methods that I've listed here. All of them are standardized by ASTM. And so the first one is Windsor probe, where you would basically fire a probe in the concrete, and the penetration depth of that probe or rod is correlated with concrete strength. Rebound hammer or Schmidt hammer, I'm sure you're familiar with it. It can give you a qualitative assessment of concrete strength, and if you calibrate it, you somehow can get, or somewhat can get a quantitative measure of concrete strength. Non-destructively, pull-out test is where you embed a rod in the concrete, and at any point in time you can pull it out by a force and correlate that force to concrete strength. But last but not least is concrete maturity, which is standardized by ASTM and is widely adopted by the industry over the past decade or so. And I'll get into the details about this method, where you would basically correlate concrete temperature with the strength of it at any point in time. Okay, so before we get into the details, as I mentioned, this method is standardized by ASTM. Not only that, but is also referred to in the ACI 318, the building code, ACI building code, where it says concrete strength shall be based for warm-up removal or shoring purposes and all that, based on the test of field cured cylinders that I discussed how inaccurate those can be, or when approved by the building official, other procedures to evaluate concrete strength. And on the commentary, it talks about the other procedures, and obviously one of them is the maturity index measurement based on the ASTM C1074. And this is standard ASTM C1074 is a standard practice for estimating concrete strength based on or by the maturity method. And it's been also referred to other ACI guidelines, and most of the DOT specifications now have this standard or guideline in them, especially for fast-track projects, to use concrete maturity for real-time strength monitoring in the field. I've listed the state DOTs where maturity has been accepted in their specifications, and obviously Iowa has marked them. So this gives you confidence in when you're working with these with the DOT projects to be able to leverage technologies based on this method. Also, over the past 5 years, I would say more and more engineers are becoming familiar with this method and are accepting it. Again, they're getting confident that this method is working well, and they can gradually move away from field cure cylinders to these non-destructive test methods, and in particular, the maturity method. Okay, so what is the basic concept behind concrete maturity? Well, it's a unique relationship between the maturity index, which is a function of concrete temperature and time, and concrete strength for a specific concrete mixture. So it's a relationship between maturity index. I'll explain how to calculate maturity index, and concrete strength, and this relationship is unique for each concrete mixture. So you need to calibrate or make this correlation for every mix that you are using in your project. Okay, so the concept goes back to early 50s, where Saul actually published a paper and defined the maturity rule by stating that concrete of the same mixture at the same maturity, which is basically a function of time and temperature, has approximately the same strength, whatever the combination of temperature and time go to make that that maturity up. So if you have high temperatures and you can gain maturity index at lower times, you'll achieve basically the same strengths. So that's shown in the graph beneath. So I'm showing two graphs where concrete temperature is experiencing different profiles, but both in both situations, the maturity index is the same, and that means that the strength will be the same. So that's the basic concept of maturity. So how do we calculate the maturity index? There are different methods to calculate the maturity index of concrete, and I'll later show you how to correlate it to the strength. But let's just start with the calculation. The first method, there are three methods that I'll explain. The first method is Nurse-Saul equation. So imagine that you have recorded concrete temperature as it's cured in the field, and this will be the graph, obviously getting affected by your curing conditions, the ambient conditions. And when you record the concrete temperature, then you have a concept that is called datum temperature, or T0. And datum temperature is a temperature below which we are assuming that there's no strength gain. And to calculate the maturity index, basically, at any point in time, you simply calculate the area underneath the temperature curve. So the maturity index, based on the Nurse-Saul equation, is the area underneath the temperature curve at above the datum temperature. So that's a calculation that you can simply do, and there are many functions to do that simply on your computer or on your phone even. So that will give you the maturity index based on the Nurse-Saul equation, where M is the temperature time factor. So you may have heard this term, temperature time factor, or TTF, that refers to the maturity index calculated based on the Nurse-Saul equation. And TA is the average concrete temperature, basically at delta T interval. T0 is the datum temperature. And as I mentioned, is the temperature below which we're assuming no strength is developed, and ASTM, as a rule of thumb, gives you 0 degrees Celsius for cement type 1 to be used as a datum temperature, or 32 degrees Fahrenheit. Traditionally, it's been taken although as 14 degrees Fahrenheit or minus 10 degrees Celsius. And delta T is the time interval. And so that's the first equation. The second, before we go to the second equation, so we calculate the maturity index, and after that you need to correlate it to the strength. So the correlation is basically a logarithmic function that correlates the maturity index calculated at 5 different times with the strengths at those 5 different times. And that, I'll get into details of this logarithmic function at the end of the equations that I'll explain. So the second equation is our Arrhenius equation. It's a bit more complicated. We basically take the area or the temperature profile, but we have other parameters that are calculated or used in the calculation of the maturity index, simply referred to as the equivalent time in this equation. And the equivalent time, or the maturity index based on the Arrhenius equation, is basically using this equation where we have Q as the activation energy. So I won't get into the details of that. And TA is the average concrete temperature during that delta T. TS is the specified temperature, and obviously delta T is the time interval. So it's a bit more complicated compared to the Nurse-Saul equation, where we simply calculated the area underneath the temperature curve. But this will give you the equivalent age, and it considers the effect of temperature on the evolution of strengths more accurately at the earliest stages, especially. The same way as the Nurse-Saul equation, we correlate the equivalent age, or the maturity index, with the strengths of concrete at 5 different times to give us the logarithmic function of correlation between the equivalent time and strengths of concrete. So that would be your correlation. The third equation is not mentioned in the ASTM. It's, the first two are part of the ASTM standard. The third equation is mostly adopted in European market, and it's called weighted maturity. Again, the same way, we're taking the temperature profile of concrete. We have datum temperature, and we calculate the weighted maturity index based on this equation, where We have the maturity index or weighted maturity. TK is the hardening time of concrete. T capital K is the hardening temperature. And there's a parameter called or a C value of cement. So in the weighted maturity, they're actually considering the strength development in different cement types at different temperature conditions. So they are more accurate from that perspective. And the NK is the temperature dependent parameter based on T. So this is weighted maturity in the same way. We correlate the weighted maturity index with the strength of concrete at 5 different times, and that gives you a logarithmic function where you can basically curve fit the A and B parameters in your calibration curve. Okay, so before we get into how we actually calibrate the mix, I would like to have the poll questions. Tom, if it's possible.
You want that first one? What is the advantage?
Yes. So
give everybody about 30 seconds to answer that poll question. All right, we're going to go ahead and close it and share it.
Okay. Okay.
Aali, are you seeing the results?
No, I can't.
13% answered it offers a real-time method to estimate concrete strength, and 88% responded all of the above.
Okay, the answer is all of the above. So concrete maturity can be used obviously to monitor real-time strengths of concrete on the job site, and also obviously that's something that you can leverage to optimize the scheduling of your construction operations. And so we can also do the second question.
Okay. Again, we'll give everybody about 30 seconds to respond. Okay. I'll share it. 100% said temperature.
Perfect. Yeah. So that's the only main parameter that is measured in the calculation of concrete maturity. So awesome. So we can go to the third one.
Okay, we'll go ahead and close it and share it. We have 86% said true, 14% said false.
Okay, so true is correct. So no matter how the concrete temperature is evolving over time, depending on its ambient condition or curing condition, if you achieve the same maturity index, which is the combination of temperature over time, your strength will be the same. This is the basic concept of concrete maturity. So let's do number 4, the question number 4 as well.
Okay. About 30 seconds. Okay, we'll close it and share it. Nobody said the freezing temperature of water. 14% said the surface and core temperature differential. 71% said the temperature below which no strength is developed. And 14% said the curing temperature of concrete.
Perfect. So yeah, the correct answer is C, the temperature below which no strength is developed. It can vary from mix to mix, but as I mentioned, the rule of thumb, ASTM gives you 32 degrees Fahrenheit for cement type 1, and most people are using that as a good guideline anyway. So perfect. So let's do number 5 before we go to the rest of the presentation.
Okay. About 10 more seconds. All right, close it and share it. 100% said A.
Awesome. I'm really impressed. So this was a bit more technical. So that's exactly correct. And because of that, Nurse-Hall equation has received wider adoption in the market. It's simpler, faster to do, and I would say more than 95% of the cases, people are using Nurse-Hall equation for the maturity calculation. Perfect. So let's, now that we know the concept behind maturity and different ways of calculating the maturity index and correlating that to strength, let's see how we are actually calibrating a mix. So, okay, let's go here. So the calibration of the mix is, as I mentioned, involves measuring the maturity index. But to do that based on the ASTM, you basically need to cast cylindrical specimens from your mix that is going to be used in the field. So you know, say in your project, you're going to use 3 or 4 mixes, and you know the exact mix design, or you can ask your producer. You can do this calibration ahead of the time to get the calibration parameters ready for your actual job site pour. So in the calibration, you cast 15 cylinders. These 15 cylinders are used for strength measurement. These are cast, as I said, from the same mix that is going to be used in the field. You cure them in lab conditions, so they don't have to be in the field conditions. They are cured in the lab conditions, static conditions, and you basically break these cylinders at 5 different times. So I put 1, 3, 7, 14, and 28 days, but these 5 times can be dependent on your time scale. If you're working with the highly strength concrete and you're only interested in the first few days to open your forms or pull cables, you can spread out these 5 times during the first, say, 3 days. So you would do 12 hours, 24 hours, 36 hours, 48 hours, and so on and so forth to get more accuracy during that time period. So pick any 5 times during your time span of interest, break these cylinders at those 5 different times. You know, the same as any other break test, you can break 2 cylinders, and if the results are the same, you move on to the next day. But if they're not the same, you cast the 3rd cylinder and you take the average, basically. In parallel, you would cast 2 extra cylinders, and these cylinders are used for temperature monitoring. So you would put the a temperature sensor inside these two cylinders and keep them in the same condition as for the rest of the specimens. So they'll be sitting in the lab conditions and the standard cured conditions, and the temperature sensor will pick up the concrete temperature evolution over time in that condition. So that will give you the temperature graph of concrete over time in lab conditions. And now what you would do is that at those 5 different times that you broke cylinders, at exact corresponding times, you can calculate the maturity index. So whatever method you pick from Nersol or Arrhenius or weighted maturity, it doesn't matter. At the equivalent time, you have your temperature graph and you can calculate the maturity index. So you have 5 strength values, and the calculation based on the temperature will give you 5 maturity index values, and you can plot them like this. So on the left, actually, this is it's a lab in Seattle where 4 different mixes are being calibrated, so that gives you an idea about how things would look like. And on the right, we have plotted 5 different strength values that we achieved, and versus 5 maturity index values that were calculated based on the temperature of concrete. So when you have this curve, you can do a curve fitting of the logarithmic function. So you have the F prime C and you have the M, which is the maturity index. And based on the curve fitting, you can calculate the A and B parameters. And A and B parameters are the calibration parameters for your maturity curve. So there you go. So this would be your correlation equation or calibration equation, where you have A and B as the actual numbers. And from now on, if you have the maturity index of that concrete, you basically plug that maturity index value in this equation, and you'll get the strengths on the left side. Okay, so how this is being used in the field. So as I said, the maturity concept goes back to early 50s. The standard was developed more than 30 years ago and has been used in the field since then. How people are using it, well, basically varies as technology is evolving. In most cases, you can simply embed a temperature sensor inside the concrete. So this could be as simple as a thermocouple that you put in the concrete in the field. You can drag one end of the cable outside the formwork, connect a data logger to it, and basically record concrete temperature as it's cured in the field. Or you can use maturity loggers like the one that I'm showing here. These systems have a battery in them, and they record temperature, and at any point in time you come to the structure, you connect your data logger to the end of the wire, and you can collect data of concrete temperature after pouring based on the curing temperature in the field. And this is also a multi-channel thermocouple that you can thermocouple reader that you can connect to multiple thermocouples and collect data from different parts of the structure as the structure is being cured in the field. So very simply, you collect concrete temperature or record concrete temperature in the field. Then you have your calibration equation or your curve. In the past, people would print this curve and go to the field, record concrete temperature in the field, and based on that, at any point in time, as you know how to do it, you can calculate the maturity index. So you can calculate the maturity index of the concrete in the field. You go on this curve, and based on this curve, you can get your strengths. And if you have your equation parameters curve fitted, you don't need the curve. You just put the maturity index in the equation, and you'll get the strengths calculated in that equation. So this is basically how maturity is used in the field. But what we have done is that with the investments that have been happening in the electronic side and the mobile app, we've made the maturity index calculation and data collection and analysis a lot simpler than just having a wire connected to the sensor and data collection and going to the curve and calculating the maturity index. So the way it works is that you basically have a sensor like a smart rock sensor that is fully embeddable in the concrete. The sensor has two parts. The end of the cable is where the temperature is measured, and this box is where the temperature is recorded. There's a Bluetooth antenna here as well, and the battery that is sufficient for about 4 months. Everything is fully embedded in the concrete. So you basically pour concrete, no wires are coming out, so you don't need to worry about the wires get caught or data loggers get damaged. And then after that, at any point in time, you can walk up to the structure with your phone and connect to the sensor wirelessly and download the data. On the phone app, you then can see all the results in real time. So that includes real-time temperature, min-max values. The maturity index is calculated automatically, obviously, as you are in that point in time. And based on the mix that you have in the app, it also calculates the strength. So you can have multiple calibrations embedded in the app, and that's 5 pairs of numbers that are strengths and maturity. By selecting that mixed name, the app automatically calculates the maturity index and correlates the strengths, the temperature of your in situ concrete to its strengths. And in the app, you can organize your project into different floors and different or sections and different sensors within those sections and label them based on their location. So when you connect to the sensor, you know exactly what corner of the structure is behaving and performing. So you can make decisions, for example, to move heaters from one corner to the other corner, or you can start from one side on formwork removal, and so on and so forth. You can also have graphs of temperature and strength over time, and the app also, the mobile app, automatically creates a PDF report which can be exported easily. You can sign it off and as part of your documentation. And the other thing about mobile technologies and mobile apps is that you can add team members for live data sharing. So anyone who's on that project will get the results in real time, whether they're in the office or outside the project. Also, with these wireless technologies, you can have remote data monitoring, where in the morning you'll be brewing your coffee and you can see what's the strengths, and based on that, call the appropriate crew to come on the job site to do the next step of the work. So these technologies like a smart rock save a lot of time from sensor installation, data collection, data reporting, whether it's simply temperature and curing conditions or strength information and hardening behavior of concrete in your pour. On top of that, all the data is backed up on the cloud, so you can basically have an overview of your projects, how many projects you have, how many sensors. You can look at how different projects are going on, and you can look at the data analytics and on this web-based dashboard. There are more features that are available on the dashboard, like strength prediction is one of them, which is a great advantage of the concrete maturity. Assuming what will be the temperature of concrete over the next few days, you can simply calculate the maturity index based on that. So you can either say, my concrete is going to be exposed to ambient condition and is going to mimic the air temperature, or I'm going to cure it with the heaters or heat it up with a heat blanket so that I can have a constant temperature of 20 Celsius or Fahrenheit, like 50 Fahrenheit or 60 Fahrenheit, based on the future temperature assumption, as you know, using any of the maturity equations, you can calculate the future maturity index. And knowing the future maturity index, you can put it in the same equation and estimate and predict essentially the strength of concrete tomorrow or 2 days from now. And that will give you an idea how things will evolve for better planning in your project. So that's I guess until now. So I think, Tom, we can do the number 6 on the poll questions at this stage.
Okay, about 30 seconds. Ten seconds. And closing it. And sharing it.
Oh, I can see the results. Yeah.
You can see it?
Yeah, I can now. Yeah, so it's C number C, so perfect. So that's exactly correct. So this is for each mix, as you've all answered correctly, that you need to calibrate your mix so that you can have that calibration and use it in the field. Okay, let's do number 7.
Okay. There you go, about 30 seconds. Okay, I'm going to close it and share it.
Okay, that's perfect answer. So anything that is dependent on knowing your in situ strengths can be optimized by the maturity sensors. And the wireless maturity sensors are making it even easier than before to remove the hassle of adoption of the method in the field and basically remove this one more hassle from your job site, so you can focus on more important stuff. Okay, let's do number 8 as well before we go to the rest of the presentation.
About 5 seconds. All right, there you go.
Okay, so some of you answered number 1. So this was a bit tricky, the question. So the key is that it says predicting future strengths. So near-stall equation parameters are obviously used in, whether you're doing early or real-time strengths monitoring or any future strengths monitoring, but just doing using the maturity data for predicting future strengths, you need the future temperature of concrete, which is the number 4. So the correct answer is number 4. Although you're using the Nurse-Stall equation or any other equation for that matter, but you basically need to predict the future temperature of concrete, whether it's cured at your controlled conditions or going to be exposed to ambient conditions. Excellent. So we'll continue the rest of the presentation. Okay. Okay, so I explained the recent advancements that have been happening in this field, and obviously smart rock sensor is one of them that can be used to help with the optimization of your schedules. We released this sensor 3 years ago, more than 3 years ago, and so far it's been used in more than 4,800 projects worldwide, anything from high-rise to mass pours to fast-track projects or concrete pavement in 45 different countries. And contractors see immediate value, unlike the conventional methods where there was still a hassle of wires and data collection and data analysis. The ease of use of Bluetooth sensors and mobile app is something that is very attractive. And obviously, as a result of implementation, contractors see at least half a day or a day of time saving per pour. So that's very significant for them. Okay, so just an overview, or maybe summarize the maturity. Some of the benefits of the maturity method include anything from continuous real-time results, where obviously you get the strength evolution information over time, as opposed to breaking cylinders that gives you one data point at a specific time, and if you run out of cylinders, you start drilling cores into the structure. The non-destructive maturity method gives you a continuous result over time in real time, and that's really valuable. It captures exact curing conditions. So if your concrete elements are different in terms of thickness or conditioned in different conditions, even though within the same pour or in the same slab, but they may experience different curing conditions at the corner or center of the slab. So maturity can easily capture that. Its results are basically alterable. So these are results that you can rely on. They're not getting basically damaged. The sensor is not damaged. They're secured in the concrete, so you can, any point in time, you can go back and refer to them if you have any doubt. And it captures variations across the structure. So again, similar to the second point, that's information that you can use. We were actually on a structure here in Canada where one side of the structure was exposed to a river, and the other side was exposed to the land. And using maturity sensors, these wireless maturity sensors, the contractors noticed that the face of the structure, or the side of the structure facing the river, is not gaining enough strength. So they immediately looked at the results and noticed that it is experiencing lower temperature values, and they obviously realized that the cold air coming from the river side is what's causing it. So they moved the heaters towards that side so that the strength evolution happens more evenly. This information, whether you're basically using maturity or just the simple temperature monitoring itself, can be used for your thermal control planning and curing planning. And in combination with the strengths, you can have a better assessment of, especially in mass pours, if you want to protect concrete or how much gradient you can allow in the concrete structure to happen based on the strength and temperature evolution in real time. And it obviously, knowing that detailed information with local strength variations can significantly improve safety and lower risk in your job site. One aspect of it is actually simply not having wires sitting around helps with the safety aspect of your workplace. And you can deliver projects faster to the owner, and obviously the more happier the owner, the more projects he can get. We had a project where it was a hotel, and the contractor finished it a month earlier, and they were able to rent out the rooms months earlier. So you can imagine how much cost saving that brings to the owner. So there could be some negotiation incentive there as well. It is obviously higher cost for the sensors, but the time and cost saving associated with the formwork removal, those operations, as well as the project finishing itself, it overweights the cost of the sensors. Okay, so there are some case studies and examples that I would like to discuss here. So the smart sensors in particular have been used, as I mentioned, worldwide in 4,800 projects. Most notably, Vista Towers in Chicago, which is about a 100-story tower, all post-tensioned. Basically, they relied on smart sensors to know exactly when they can pull the cables, and they completely eliminated the field cure cylinders, for that matter, to speed up their process. Encore Resort and Casino in Boston also used our sensors, and they were able to also finish the concrete part a month earlier ahead of the schedule, knowing that information. And obviously all this is documented, recorded, and it's something that you can always refer to that and improve your efficiencies as you can review how concrete is evolving and curing over time. Some detailed case studies, McCormick Hotel, again in Chicago, is a 41-story post-tension concrete floor, and they had two 11,000 square foot placements per floor, and they used 3 smarts per deck placement, and they were checking the sensors the first thing in the morning, and that helped them. That information helped them at least save 1 day per cycle per placement, and that was about 16 weeks in total saved during the project. So you can imagine how much cost saving that has for that contractor. And these are just some examples, pictures of the structure and where the sensors were installed. Mass pours, as I mentioned, although you're basically concerned with the temperature gradient, and you can use smart rock sensors for monitoring temperature and calculating the gradient in real time. But another advantage of combining that with maturity is that if your strengths is developed faster, or if you can capture the strengths development, you can talk with to the engineer, and there are guidelines in the ACI and the building code that would allow you more gradient if you have high strength values. So although you may have a specification of 15 degrees Celsius, you can go up to 20 degrees Celsius if your strength is high enough. And that's something that you can work out and basically leverage to minimize the duration of heat curing or keeping the concrete cool in the summertime. And again, this is another sort of set of pictures where you see how sensors are installed in mass pours. You can install them the day before where you have heavy caging, and the next day you would pour basically concrete. Concrete pavement is also a very unique application for these wireless maturity sensors. You're dealing with remote conditions. This was a piece of highway pavement that had to be repaired almost 100 kilometers away from the lab. So that would take them obviously a long time to pick up the specimens, so the field cure cylinders, and go back to the lab and break and give the results. So they started using the maturity sensors in this pavement repair, and they were able to monitor strengths in real time and open the lanes to traffic much quickly. And obviously the MTO in this particular case was very happy to avoid congestion and traffic in the highway. And this is another example. So in this case, they didn't have rebar, so these sensors that are typically twisted and tied around the rebar, in these cases, they put them on the dowels in the pavement. Okay, so obviously, like any other method, maturity has limitations, and you have to know these limitations. And when you're using any test method for that matter, keep that in mind so that you don't get false positives or results that not accurate. So the first one is mix change. As I mentioned, maturity calibration or correlation is specific to each mix. So if you have different mixes, you obviously have to calibrate all of them. But if you have the same mix, and for whatever reason, I don't know, the driver is adding more water than needed, or it's a cold day and the producer is adding accelerators in that mix, it's not going to be the same mix. So the maturity calibration is not going to be valid. So any change that is happening in the mix, you need to be aware of that and be cautious. If the mix is changing, you can't use that maturity calibration. If you're expecting any change in the field, say you're expecting that the water is going to have variation, the water content, maybe you can calibrate the same mix with different water content ahead of the time. So as you experience different water content values, you can use different maturity calibrations to accommodate for that. The second thing is that datum temperature. Obviously, I gave you the rule of thumb based on ASTM, but this is, again, mix dependent. If you want to be super accurate, you can calculate it. But most of the time, the datum temperature that is given to you by the ASTM is giving you the conservative value. Maturity is not designed for long-term strength monitoring. So it's not replacing the 28-day strengths. You still have to do the standard cured cylinders. And if you are interested in knowing the strengths of concrete more than, I would say, 14 days, you need to break cylinders. Maturity is designed and developed for earliest stage strength development, where you're dealing with formwork removal, post-tensioning, or things like that during the first week or so. It also assumes that you have adequate curing. So if you don't provide enough moisture to your concrete and concrete dries out, it cannot be captured by the maturity equation. Maturity equation is simply looking at the temperature of concrete. So you need to keep that in mind. If anything else is happening in the concrete that is not being able to be captured by temperature, you need to be careful. So if the other thing is placement and constellation. If you're not compacting concrete well enough, it cannot be captured by maturity, because maturity is only monitoring your temperature, and it cannot capture the voids or other things that are happening in the field. So just be mindful of that. And obviously, you need to verify calibration. So from time to time, you may see stuff that are not captured by you. So you need to verify your calibration, even if as simple as cement changes over time, or the batching plant that the producer is using is different from the original batching plant. So from time to time, verify calibration, especially at the beginning. Monitor concrete strengths and verify it with field cured cylinders. And when you're confident, you can completely eliminate field cured cylinders. And the verification is simple. You basically cast 3 cylinders from your mix that is delivered to the job site. You can take these cylinders back to the lab, monitor temperature in one of them, and based on that temperature, you can calculate the maturity index, and on your curve, you can see the strength. And the remaining 2 cylinders, break those cylinders, and that gives you another strength value. So if these 2 strength values are more than 10% apart, that means you need to calibrate your mix. And that's basically the verification purpose or the procedure. And as I mentioned, to start with maturity, initially there's some skepticism among the community, and also in particular engineers who've been using cylinders for a long time. So what we suggest is that start with monitoring concrete strengths using the smart concrete sensors or smart sensors, and detect the time at which the estimated targeted strength is achieved. So you can monitor the strength in real time using these sensors. And then at that point, send the cylinders, the field cured cylinders, to the lab, break those cylinders, and that would verify your maturity evaluation. And based on the approval of the break test, you can gain the confidence of the engineer side, your side, and for the next pour or the next pours, you can minimize the number of break tests or completely eliminate the field cured cylinders. So that was it from the slides. We have 2 remaining poll questions, so we can do that before we conclude the webinar. So the first one, Tom has it on the screen, I guess, yeah.
All right, 10 seconds. Okay, close it and share it.
Okay, yeah, so the correct answer is false. If you use a different concrete mix, you need a new calibration. It doesn't matter if it has the same water cement ratio or the same slump or the same amount of cement. It's a different mix. So you can have the same water cement ratio, but with different aggregate grading or different cement type or different admixture, you still need to do a calibration. So the last poll question.
Okay. All right, we'll close it and share it.
Okay, so this was a bit tricky. So obviously, so when you have your maturity verified and checked and confirmed in the field, initially, obviously, you need to discuss it with the engineer. But before that is you need to ensure that there are no other conditions that cannot be detected by maturity. So your calculation may show a particular strength value, but your concrete may have not been compacted well, or it may not have been cured with enough moisture. So those conditions obviously affect the strength that cannot be captured by the maturity. So if you verify that there are no other conditions, then you can submit this to your engineer and say, we have achieved the targeted strength, and move on to the next step. Perfect. So that concludes the poll questions, and I guess, Tom, over to you.
Okay. All right. Great information, Aali. We certainly appreciate the time that you put into developing and delivering this webinar. It's new for us as an organization. We're glad to get some new stuff out to our members. Aali, if you can go ahead and jump over to that last slide for me. Oh, let me hide this. Let me hide that question. There we go.
Okay.
All right. So we're kind of getting accustomed to using these webinars to promote future trainings that we have coming up. As you see on the screen, we have Target Value Delivery Workshop coming up. We're bringing in Christian Peichel from the Realignment Group. He did the Lean seminar that we did a year ago. We've done the AGC Lean Education Program, and this class actually counts as continuing education for that credential through AGC of America, and also provides AIA continuing educations if any of you are architects out there. And feel free to share this information with anybody in your office that feels like you're on that lean journey, or you want to take another step in your lean journey. This is a great opportunity to do that. You can just shoot me an email at that email there that you see on the screen. We don't need the formal registration form, but be a great program. We've got about 35 registered in it. We're excited for that one. So if that's something that interests you and your team, definitely take a look at that for us. So with that, I'm going to go ahead and conclude today's webinar. Aali, again, thank you very much for your time putting this together. Everybody online, be looking for that email from me this afternoon, and please give us some feedback on those evaluations. With that, we'll go ahead and sign up. Thank you, everyone, and have a great day.
Thank you. Have a great day.